Recording is rolling. It's Wednesday, May 25th, and I'm gonna tell you guys all about quantum mechanics. So it took about a week with my honor students to what we did was put together this quantum mechanics journal on a list of quantum mechanics topics. So I'll go over that with you guys, and I've got some demos lined up, so I'll switch back and forth, and you guys get this version of it. Oh yeah.
For calculus for math.
Hold on, let me pause it. Oh, all right. Okay, so all the physics that you guys learned here falls under the umbrella of classical mechanics. So we're talking about macroscopic size objects. But when you get down small enough, so first question here is like how small is an atom? A lot of those classical physics rules go out the window, and a new set of rules pops up that has to do with wave particle duality and existence and probabilities, right? Is a lot of things you'll see. So it's probably a good starting point to say, well, how small are we talking about? Right. So this I dug up this TED video that makes this analogy of sizes of an atom to the size of a grapefruit, measuring the size of grapefruit. It's like a softball size you could hold in your hand, right? Okay. How big is an atom compared to that? Well, it'd be kind of like about the size of a blueberry compared to the size of the entire Earth. So it'll give you a sense of scale there, right? And within the atom, and I'm sure you guys all know the model of like the nucleus is in the center and surrounded by a bunch of orbiting electrons. Now we're gonna get back to that. We're gonna because that model, well, we're gonna get more a little bit more specific on that. But the nucleus of the atom has almost all the mass. And how big is that compared to the size of the entire atom? Well, it's kind of like having, say, a marble in an entire like football stadium, right? It would be like where the protons and neutrons are, right? And therefore, like most of the mass. And all those electrons creating the electron cloud takes up well most of the rest of the atom. But those electrons, you might think of them being like particles, like maybe that's like some model you saw in a textbook back in the day. But they really have more like wave type properties. And most of an atom is actually just empty space. It's actually most matter is just like empty space, right? You like crunch it down, just like a neutron star or black hole size, and make it more dense. But yeah, everyday world. Right? Yeah, so how does anything just like not collapse on itself? Well, because of electrostatic forces, right? So electrons push against electrons, right? Like me holding up this pen here. Right. Okay, so that's kind of the size that we're talking about. Right. So where does the quantum mechanics kind of start? And I think there's a good case to make going back to 1887. There was this experiment done by this guy named Heinrich Hertz. Did stuff with a radio wave. Oh, like Hertz, you guys know is the unit for frequency. Okay. And he was trying to capture energy from light, right? So like early PV cells, this sort of thing. And one thing he did was he would shine a light on a PV cell and get no energy from it. I said, okay, so no problem. I know classical mechanics, light has been determined to be a wave. So maybe if I make it more intense, I can get more energy from it. At some point, I'll get energy from this PV cell. Because you do need an initial amount of energy to overcome, it's called the work function, to have electrons jump a gap and then create the initial circuit on a PV cell. So it's not okay. But the problem was that if he wasn't capturing any energy, it didn't matter how intense he made the light to make it like super bright. He was just getting nothing. So well, what if I change something else? So change the frequency of the light. Say going from like red light to blue light, that would be an increase in frequency, right? And then he started to get energy on this PV cell. In fact, it was a linear relationship between the frequency and the energy captured, which was really weird. This was not expected. This really is something called the ultraviolet catastrophe, which maybe another branch of the story to go through here. So, well, don't know exactly what to make of that, but I've got this data. And the data really does line up in a line like this. So it's a direct relationship. By the way, the slope of this line eventually something called a Planck's constant. It's one of the fundamental constants of the universe. Tiny, tiny, tiny number. Here it is right here. It's like 10 to the minus 34 joule seconds. So crazy small number, but there you go. Right, so then along comes Albert Einstein in 1905. This is Albert Einstein's miracle year. This is when he publishes a paper on like, special relativity and a few other ones. And he also looks at this particular experiment done by Hiram Hertz and says, you know what, I'm going to interpret what's going on here as light that we thought was a wave all along actually might end up having particle-like properties. So this is the first hint at wave-particle duality. So the story with light is, if you go back hundreds of years ago, there was always a debate of what is light fundamentally? Is it fundamentally wave or fundamentally particle? Now, waves have certain properties and particles have certain properties, right? One of the properties of waves is if you shine it through, for example, here, so let's say you have a piece of cardboard and you cut a couple of slits in it, right? You shine a light through. Well, you're going to get some diffraction, right? And then there's going to be interference of like two wave patterns. So you get an interference pattern. You guys see some of this stuff later too. So, okay, so now we've got like a characteristic of what makes a wave. I'll show you guys an animation later when this is all going to come back. Okay. And then a particle, of course, is more like just like a point mass, right? So you throw particles through two slits, you should get like just two bands right on the other side, not an interference pattern. Okay. Now, there's this experiment done early 1800s by guy, his last name is Young, and he did this double slit experiment with light. Said, "Oh, hey, so light has interference patterns, totally wave." Right, we'll move on from there. Einstein says, "No, actually, this experiment right here, Hiram Hertz, indicates that maybe light has more particle-like property." Right? And I can think of it like this. Let's use this garden hose model. Okay, so let's say you have a bunch of marbles going through a garden hose. Ooh, a bunch of marbles. So it'd be like a bunch of particles, right? Let's say every marble represented a particle, like a point mass. Right? Maybe like an energy packet, right? And this is where the word like photon comes from. Einstein's term for what a particle of light would be, a photon. By the way, Isaac Newton had thought that light was in particles all along. He called them corpuscles, but Einstein went with photons, so that's what we get this word. Right. So you say, well, if these marbles are rolling through this garden hose, they could be rolling out with a certain frequency, like don't. Versus if you had higher frequency, it would like all these marbles rolling out here. Ooh, that'd be like more energy per unit time, right? Hey, like a higher frequency, right? Well, we replace those point masses with a wave, like a low frequency wave versus high frequency wave. And that's what could explain this photoelectric effect. This, by the way, is what Albert Einstein actually got his Nobel Prize in Physics for, was explaining this photoelectric effect. Like weirdly enough, not what he's most known for relativity, but for photoelectric effect. Okay, so now that we got this photoelectric effect, we got this dual nature of light. Light has both wave and particle properties, right? And this, again, the slope of this energy versus frequency graph is what's called Planck's constant, 6.6 times 10 to the minus 34 joule seconds. Crazy small number. One of these fundamental constants in nature that kind of like the universal gravity constant or the speed of light. Nobody knows why the number is what it is, but we can measure it to be that number, right? And so while we're at it, let's look at like how small can you actually go in the universe? Now, this part, I can't explain why this is, but I just read this to be the case, so I'll just tell you guys and look more into it if you want. But you know how if you look on your computer screen, it's like, okay, I see a fluid image, blah, blah, blah. But you know, if you look small enough, everything's really like pixels, and at some point, like just points of light blinking on and off, like red, green, and blue lights. Okay? Well, is the universe kind of like that? What is the universe? Is the universe like completely fluid, or is it pixelated at some point? Well, there is actually a smallest meaningful length unit of time and smallest meaningful unit of length that you can talk about when you get into physics. And it's crazy small numbers. So 10 to the minus 44 seconds for what's called a Planck time, and 10 to the minus 35 meters, what's called a Planck length. I mean, this Planck time, just to pick one of them, is so incredibly tiny that there are more Planck time in a single second than there have been seconds in the entire history of the universe. And it's not even close. So we're talking about crazy small amount of time. But if you were try to like subdivide this into like what's like a quarter of a Planck time or a quarter of a Planck length, those are considered to be like meaningless in quantum mechanics, just because well, again, I can't explain why, but that's what scientists came up with. By the way, if you take this Planck length, divide by this Planck time, you actually do get the speed of light. That's kind of interesting. Oh, here's an analogy for Planck length. The ratio of a Planck length to the width of a human hair is the same proportion as the width of a human hair to the diameter of the observable universe. So we're talking about crazy, crazy small, but there you go. So the universe, a certain way you could argue is kind of pixelated. Okay? All right. Along comes this guy named de Broglie, and is thinking about this wave particle duality. He's looking at some of the equations that are lying around that are pretty new. Okay, we got this mass energy equivalence fell out of Einstein's relativity papers. We got momentum for describe particle behavior. We got this wave equation, right? Frequency is speed divided by wavelength, and I have speed of light here for electromagnetic waves. There's also this new formula that popped up, E equals HF, which is basically this right here, right? Well, minus this work function y-intercept. Okay. So he says, "Huh, I wonder if I can combine these formulas and get something different out of this." He does this and gets what's called the de Broglie wavelength for any particle. Ooh, look at this. We got a wavelength here. We got a mass and a velocity like that could refer to a particle over here. Huh. So now he's mixing and matching things. So wave particle duality. So now we have an equation to say what is the wavelength of any particle. And you can do experiments say, oh yeah, actually, this is sort of the case. I remember even there was I was taking physics in college. They said, like, what's the wavelength of a baseball moving at such speed? So I said, okay, you plug in the mass of baseball, speed of baseball, Planck's constant, which is crazy, crazy tiny. Remember, that's like 10 to the minus 34. Okay, and you get tiny, tiny wavelength, but it would be calculatable. Okay, so where would this ever really matter? Because get big enough mass and the wavelength becomes negligible to the point that, well, what does ever really matter? Okay, well, it could matter if the particle mass is really small. For example, an electron. Okay. Do you guys remember this type model from your chemistry class? Right? Yes. So electron configuration, right? So the 1s suborbital can handle 2 electrons, so that'll take care of hydrogen, helium, and then if you move up to lithium and beryllium, well, now you need another, right, like the 2s, and then go on to what comes after that. I think it's like boron and carbon, and it goes on from there. Okay? So. But why is it that electrons only occupy certain suborbitals? Sorry, well, why can't they just exist anywhere? Because think about the model of an atom being like, okay, we've got this positive charge nucleus, your protons and neutrons. And we got electrons rotating, going around it, kind of like planets in the solar system. Well, planets in the solar system, they can be at any distance from the sun, but that's not true for electrons and down the atomic scale. They have to exist in these certain suborbitals. Why is that? Well, the de Broglie wavelength exactly explains why this would be the case. Because if you plug in a tiny, tiny mass of an electron, move it, right? Then even Planck's constant divided by a tiny mass, well, that will give you a wavelength that is significant enough to explain this. So an electron going around the nucleus of an atom has to fit an integer number of wavelengths. Like here I'm showing 5, right? 5 wavelengths. Okay, but you could have like 4 or 5 or 6 or 7, but you couldn't have like 3 3/4 wavelength. It has to close in on itself. Right? Huh, so that's interesting. And that explains so much of chemistry comes down to this, which again is based on this quantum mechanics, this de Broglie wavelength. Okay, so to pick one example, just one phenomenon, what does this have to do with anything? Is why are some materials, for example, glass, transparent? Okay, so. And glass is only transparent to certain parts of the EM spectrum. And like these walls right here, like why can't we see next door, right? Well, it's not transparent. Like these walls are not transparent to the visible part of the EM spectrum. There may be other parts of the spectrum, like the X-ray part. If we had X-ray vision, we could see through to the other side, right? What about that glass right there, the little glass window on the door? Okay. So visible light can get through there, but maybe not infrared and maybe not even UV, right? Just like certain parts. Right? So what explains this? Okay. So if you look at this electron configuration for glass, now glass is silicon dioxide, right? SiO2. Well, it's like 99% silicon dioxide, so we'll just call it that. If a photon in the visible spectrum hits those SiO2 atoms, or I should say molecules, right? That is actually not enough energy to lift one electron from one orbital to the next, which is normally what happens, like for non-transparent materials, right? Photons hit it and it warms up the material slightly, it raises the electrons, but this energy gap is too large for silicon dioxide. So the photons just go straight through because they have nowhere to deposit their energy. And that's why you can get transparent materials. Okay, so now we've got a quantum mechanics explanation for why materials are transparent. Right? And that's just one example. I mean, really, the entire class of chemistry goes back to this at some, some point or another. All right. Okay, so now we've got this this wave particle duality pretty well established, right? You know what else is probabilistic is just the existence of matter at all. Now, here's where we're into something called a Schrodinger's equation. So the wave function of Schrodinger's equation. Now, maybe I'll flip the screen over and show you guys what this equation actually looks like. This, okay, let's just talk about.
Can I go to this Bridget's room real quick?
Hold on, let me pause the room. All right, so there you go. You're looking at Schrodinger's, well, different versions of Schrodinger's equation. Now, this is like crazy high calculus math. I'm looking at some partial derivatives going on here, but basically what this says, screen back over, give you its interpretation of this, is that if you want to say like where is something located down at the atomic scale, you're going to have to talk about probabilities. Okay? So this is why you guys remember what was it, a week or two back, I took you guys through statistics. You guys remember that? I want you guys to have the statistical framework going into quantum mechanics, because quantum mechanics is statistical. Like if it said, like where is like this item right here? Oh, I got the marbles. Not the little critters. But if you think about this like a point mass, think of these like point masses. Thank you. You'd say, well, they have a mass and a location, and you can plot them on a Cartesian coordinate like XY coordinates and the whole deal, right? But when you get down to the atomic scale, atoms is just sort of all spread out, okay? And there's a probability of them being at any certain location. Weirdly enough, until you measure it, right? If you have an observation, a measurement of exactly where's the electron, then it will follow. This wave function will collapse into like one particular point. So if you measure where's an electron, say like 1,000 times, right, and then you graph it, it would make a graph that looks like something kind of like this. Maybe this could be like on the next axis, right, one axis. You can see, right, there's certain places it's most likely to be, right. Now, of course, once you measure it, then it becomes like at that location, right. Hey, that kind of reminds me of maybe something like this, right? Remember, there are certain like suborbitals that electrons will land in. Ooh, this looks like it lines up kind of like different suborbitals, doesn't it? Ooh, that's interesting. Okay. Now, that whole deal about, oh, yeah, we're getting pretty close to right. When you measure it, this wave function collapses into like one reality. That brings up this unnerving idea that, well, that your observations, your measurements actually affect reality in a certain sense, right? Because like all along this class, we've been assuming that you can build some small model of the universe and run an experiment, and that's representative of some larger whole, but you can be an independent third-party observer, right? So you watch those Hot Wheels cars roll down the ramp, you break out a stopwatch and a meter stick, or you're watching pendulums swing back and forth. You can make certain measurements, but your measurements are not affecting that reality. But that's actually not the case when you get to quantum mechanics. Okay. Now hold on to this idea, because there's some other experiments that are going to back that up. Come up here. Okay. Let's look at a Heisenberg uncertainty principle class. So there's this limit to knowledge that once you get small enough, like can you know exactly where a particle is going to be and also its velocity simultaneously? I don't know the derivation for this, but let's just run with this, and I'll show you guys an experiment that's playing out. If you look at what's the uncertainty of position of, say, a particle or mass, right? And the uncertainty of its momentum, right? So mass times velocity, right? Those uncertainties have to be at least as big as this tiny, tiny, tiny number, because here's Planck's constant, h, right? That's about 10 to the minus 34, so crazy, crazy small number. Okay? So, your everyday, macroscopic classical physics experiences, you never run up against this because it's just so crazy small. But if you get down small enough, okay, then the product of these two uncertainties has to be at least as big as this tiny number. So let me switch over and show you guys a Veritasium video on this. Veritasium. Right. Present screen 2. All right, so if you're watching this video, there's Schrodinger equation. Let me dig up an experiment showing a Heisenberg uncertainty principle. There we go. Oh, got sound turned off.
Certain principle. So here I have a green laser and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted so it could be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out.
Ooh, not only does it start spread out, but do you see those bands where it's like, okay, there's obviously a dark band, or I should say a bright band right in the middle. But then there's like a band here, and then like really faint band here. Hey, that looks a lot like that Schrödinger equation model that I sketched up, right? Like there's certain probabilities where those photons could land. Right? Why is it spreading out when he's making the slit narrower? What's going on there?
Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle.
All right, he writes it out. There you go. That's exactly right there. So the uncertainty of position times the uncertainty of momentum has to be at least as big as that crazy small number. Right. So in this case, when you make that slit too narrow, then you're getting more certainty about the position. So that's less uncertainty, right, which is driving down that delta x. Right. And then when that delta x gets too small, the delta p has to go up to compensate, right, so you don't break Heisenberg uncertainty. And then that's going to manifest as direction of motion, right? Because that's what momentum could be, right? It could involve direction of motion. Right, so there you go. Okay, so we got next lined up. Oh, all right. Now here's where things take off and get like really super creepy and weird. Double slit experiment. Now there was this double slit experiment done back in the early 1800s, but we're going to build on that. So it went like this. If you shine a light through a couple of slits, you see this interference pattern in the back. Notice because actually any wave that you shine through or let go through two slits, it's going to create its own set of waves, its own set of ripples. Those ripples what interfere. You guys remember interference, like constructive, destructive? Okay, right, so you get this interference pattern. Versus if you shine through like a bunch of marbles, like, then you should see something like this, like two bands. Okay. Here's the weird thing though. If you have some kind of detection equipment to determine like exactly which let's say you're shining through like a tiny particle. This could be photons, this could be electrons, right? If you just let it do its thing, it's usually gives you an interference pattern saying, okay, well, photons and electrons have wave-like properties, so maybe that can make sense. But if you have some kind of detection equipment to determine like exactly, well, which one of these bands that's listed go through exactly, that actually changes the nature of those tiny particles. And they actually change from waves to particles, just because that information is available. Right. So this is another case of like you can't really be a third-party independent observer when you get down to quantum mechanics because your measurements, your observations actually affect reality. Right. So an observer collapses this wave function. I'll switch over and I'm not going to play this whole thing, but we'll refer to this. Okay. Right. So this guy, this animation, I bet if you go to YouTube and type in Dr. Quantum, this guy will probably come up. Takes you guys through this whole experiment. So right, there you go. So single slit, shine through marbles, great. See that double slit, marbles, get two bands. Yay. Right. How about with waves? Okay. Well, something with a single slit looks like that. Right. Double slit. Right. Shine through waves. Use ripples on water. Ooh, do you see how there's going to be an interference pattern that emerges from these two slits right here? Is this? Okay, let's check this out. Okay. So interference pattern. All right, so first few minutes of this video just explains what is the definition of a particle, what's the definition of a wave, right? Because again, like before quantum mechanics came along, we definitely had like a box for particles and a box for waves. So okay, so now we got clear definitions of what's what. Okay, they says okay, let's go down to the quantum size, okay. And now let's start firing through tiny particles. This could be like photons or electrons, just little tiny particles. Okay, okay, so single slit, yay, does that. Okay. All right, now let's bring in two slits. Okay. All right. So we get this this interference pattern. Okay. Which up to this point, maybe not super surprising because maybe those electrons are like interfering with each other. They exist spread out probabilistically according to Schrodinger's equation as they're going through both slits kind of at the same time for interference pattern. Right. Right now, the tail end of this video. Here we go. Let's bring in the measuring device. Now he's going to represent the cartoon eyeball, but I'll show you guys after this the more like proper scientific setup for this. But here's the crazy part of this video. Here we go.
Actually goes through. They put a measuring device by one slit, see which one it went through, and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently. So it was aware it was being watched. And it was here that physicists stepped forever into the strange never world of quantum events. What is matter? Particles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right, you ready to have your minds blown? Oh man, your minds are going to be blown big time.
So here's the more proper version of this. If you search on the internet, quantum eraser, delayed choice quantum eraser, I think you can find this. So he's going to give you a more detailed version of this. He says, first of all, go watch this video that I just ran through with you guys so you can get the big idea of what's going on here. Right? Say, okay, here's the definition of a wave. You should see an interference pattern. Here's the definition of a particle. You should just see two bands. Right? Oh, hey, look what we got up in the corner. Got like a laser light shining through. Oh, two slits, slit A and slit B, right? And it's bouncing around all these different mirrors, and depending on which way it bounces, blah, 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 eventually reaches its coincidence counter and either produces the two bands or the interference pattern, right? Which tells you like the nature of the original, right? Now, this is one of those videos that you have to watch like a few times, or at least for me, I'm just telling my own experience. I had to watch this like 3, 4, 5 times before it's really clicks and you see, because this is a pretty complex setup. Right? But at the end of the day, what this is saying is that if you can track which slit A or B exactly that the particles went through, then it ends up producing like the double bands to say that it's a particle. But if it ends up being ambiguous, so if it could have come through either one, then by the time it reaches the coincidence counter, it actually gives you the interference pattern, which would indicate a wave. So just by having the information as to where the particles would have been actually changes its nature as to whether it becomes a particle or a wave, right? Which is crazy. And what kind of crazy implications come out of this, right? So does that mean that, does that imply that conscious observation like somehow builds the entire universe? I mean, that's one possible implication that's on the table, right? So this can bring us to one of the craziest thought experiments in physics, which is Schrodinger's cat, which I think some of you guys may have heard of. Right? So as an example of this measurement problem, right? This measurement problem being, right, well, now you can't be an independent observer of nature anymore, right? By measuring, observing, that affects an outcome. So one of the early quantum physicists back in the 1920s, 1930s, a guy named Erwin Schrödinger. Oh, well, you guys saw Schrödinger's equation, so same guy here. Right? He was really bothered by some of the ideas that were coming out of quantum mechanics at the time. So he came up with this thought experiment to try to poke holes in this and debunk this and say, well, there's no way this could happen, because he came up with this crazy thought experiment. It goes like this. Okay? What he does is he ties the quantum world to the macroscopic world and says that there's a clear contradiction in these two different sets of laws of physics. Okay? So suppose you had a radioactive atom. Now, not all atoms are radioactive, but some are, and so they'll decay after some time. Now, that time you might refer to like a half-life, because it's probabilistic as to when it will decay. So let's say, just to tag a number to it, that this radioactive atom has a half-life of 1 hour. some atoms, it's a fraction of a second, some it's tens of thousands of years. Let's go with 1 hour, just to keep it simple. Right? So that means that if you leave it alone, come back after 1 hour, there should be a 50-50 chance that it's decayed, right? And if you, oh, I'm gonna steal this next graph, right? And after the next hour, well, now it's up to 75%. And after the next hour, now it's up to like, what is it, 88% or something, right? And every hour that passes gets closer and closer to 100% chance that it's decayed. Right? Wait 100 hours, now it's like almost certain. Right? Okay, so we're gonna tie the decay of this atom. If this atom decays, we're gonna say it sets off this whole chain of events. What's gonna do is trip this hammer. We're just gonna break this glass of poison, which would then kill this cat, which is all inside this closed box. By closed, I mean there's no way you can't see inside the box. This outside observer can't see in the box. They have no way of detecting inside the box. They can't hear the cat meowing or anything. They can't feel anything. Right? It's just completely closed system. Okay. Okay. So we close the box. Right. It's got the cat in it. We're sitting around waiting, and you might think, well, after an hour, there's a 50-50 chance that the cat is therefore dead or alive. You know, just because it's tied to the quantum state of the atom. Right. Atom decays, trips this whole process, kills the cat. Okay. Now, the quantum mechanics interpretation of this, if you think about the full implication of like this double slit experiment example, is that because atoms exist probabilistically in a state of superposition, like the atom would be both decayed and not decayed at the same time, right? But then once you measure it, once you observe it, it's going to collapse into one of those two states. Is it going to be decayed or not? Right? But before you measure it, it's in a state of superposition, right? You say, well, that implies that this whole process, including the cat being dead or alive, would also be in a state of superposition. So you couldn't say that the cat was either dead or alive after an hour. You would say that it's both dead and alive until you open the box and make an observation. And then that collapses the wave function into one of those two realities. Okay? Now, this experiment's never been, this is only a thought experiment. It's like, how could you ever really do this? Because like once you get the information, that destroys the quantum superposition state. But that's an idea that yeah, just stands up with the laws of quantum mechanics. That's what it would imply. That would be the case. Okay? So how you can tie the laws of quantum mechanics to maybe even the macroscopic world. But this raises other questions too. It's like, well, what are we kind of like the cat in the box in our own little society here on Earth? Do we keep each other in existence by observing each other? Do we need some kind of outside observer to observe us? Like what's the deal with that? Or is this completely bunk and maybe everybody's missing something else? Okay? Another phenomenon related to this is something called the quantum Zeno effect. Now the Zeno effect, this is an old thought experiment, goes back to ancient Greece. It's this idea that saying either you shoot an arrow or you're running a race, one or the other. Okay? You're trying to get from point A to point B. And to get from point A to point B, well, first you have to go halfway, and then halfway from there, and then halfway from there, and halfway from there. So maybe you never reach the finish line because you're always getting halfway. I know, kind of silly thought experiment, but yeah, who knows? It was an idea floating around back in ancient Greece. Okay? Now, of course, you guys know distance equals speed times time, law takes care of everything. Okay? But there is sort of this weird parallel idea that comes up with quantum mechanics, this quantum Zeno effect. Suppose you have like this radioactive atom, right? So it should decay out, say it has a half-life of 1 hour. After 1 hour, there's a 50-50 chance it should have decayed, right? But suppose you have detection equipment constantly observing it as to when exactly does this radioactive atom decay. It will always collapse its wave function back to the original state. And then the atom will never decay. You could wait like 10 years and the thing is just like sitting on the shelf, like, man, this should have decayed a long time ago. But with constant observation, it constantly collapses the wave function back to the original state. It goes back to some of these other ideas that you can't be a third-party observer in quantum mechanics. Your observations, your measurements are actually affecting the outcome, actually collapsing that Schrodinger equation wave function. Oh, I should say too, I should mention the term Copenhagen interpretation. Right. So maybe this is also strong evidence of that. The Copenhagen interpretation of quantum mechanics is just that. It's one I've been explaining that. Once you observe something, it collapses the wave function to just one reality, and then the entire universe moves on with that one reality. Right? But there are other interpretations of quantum mechanics that you can never like exactly test these out, or at least nobody's figured out a way. One of the competing theories is something called the multiverse theory, that maybe like this atom decays and doesn't decay, and we like the universe splits, and both of those events happen. Just the event happening that we don't see, just happens to happen in another universe. So we open the box and say, hey, the cat's alive, and the atom never decayed. But in a parallel universe, maybe the atom did decay and killed the cat, but we just aren't in that universe. Okay? So yeah, those are the main two interpretations. There's some other ones too. All the stuff I'm telling you guys, if you're really curious about it, of course, you can always search on the internet more into this stuff, right? I have to mention quantum tunneling. So remember, things exist probabilistically. Suppose you have like a barrier somewhere, right? And you're saying, well, where is an atom, right? Well, you're talking about an atom. This is probabilistically. Say you have a probability curve. Maybe there's like a 99% chance it's here, but there might be like 1% chance it's on the other side. So make 1,000 measurements, and that proportion of the time, you actually will find the atom on the other side of the barrier. Okay. Now, what is this good for explaining? Actually explains a couple of things. Electronics. I put away all my infographics. Do you guys know Moore's law? You guys know Moore's law? Okay, here, I'm gonna sketch this up just from scratch real fast. So if you look at, yeah, I had a really awesome infographic on this too, but just sketch up here. If you look at the number of transistors that you can fit onto a computer chip commercially, like economically, as a function of time. Okay. Oh, I'm going to do this too. I'm going to put this vertical axis on a large scale. So the time axis is going to be linear. So if computers, those probably come around, let's go like, I'll put 1970 right here, 1980, 1990, 2000, 2010, 20. And then, okay, so I see time increasing linear, right? But I see number of computer chips, the number of transistors on a computer chip increases logarithmically. So the numbers would go, I kind of make up numbers, but you guys get the idea. Right? We're gonna go like 1, 10, 100, 1,000, 10,000, 100,000, million. Right? So it's going up logarithmically, right? Exponential growth. Okay? And then you plot all the commercially released computer chips at different times. They line up like eerily into this like nearly straight line like this on this thin log set of axes. Okay? So sometimes you hear that. So this is Moore's law. Now, sometimes it's expressed like computing power periodically doubles like every year or 2 years or something, or there are different ways to couch it, but some version of that. Now, this is a law because it has been observed to happen. Will this ever run out? Probably so, just because at some point you just get so small, you can't really get any smaller. You just run into like the size of atoms, right? And then you run into problems like this too, like if you start using like electrons as ones and zeros to store data, well, you might get these probability problems. So there's only certain probabilities of exactly where you can find these electrons, and sometimes they'll tunnel to places they shouldn't be. Okay, there's whole cases I've seen where gives sort of a tangent example on this. Maybe it's not exactly this, but it's sort of an interesting idea. I saw the story of like this plane that's flying over, I want to say like the South Pacific or something, and all its instrumentation went absolutely haywire. And the plane barely landed, and so, oh man, we had some kind of crazy programming error or something, because we don't know what happened, but like pilots were saying, trying to do some controls, and it was saying to do other controls. They're like trying to, I forget exactly what it was, like turn the plane, and it was like change its altitude or something crazy, but they got the plane landed, everybody was okay. And what it ended up being, they eventually determined, was a cosmic ray from space had, wrong place, wrong time, hit like some file on board the plane and changed like a 1 to a 0 or 0 to a 1 or something, right? And that just like threw everything off. So yeah. But another example of tunneling that has a practical application is fusion in the sun, right? So you guys know our sun is like giant fusion, right? Fusing hydrogen and helium. But if you look at the pressures and temperatures, say the core of the sun, say, okay, so how much fusion should be going on? The numbers don't add up. Well, that doesn't really count for all the fusion until you bring in quantum tunneling. You realize that, oh, sometimes two hydrogen atoms are close enough that they can tunnel into the same nucleus, and that accounts for the rest of that fusion. So then we get sunlight on the Earth. Yeah. Oh, quantum entanglement. Okay, and here's a real crazy one here. This is what Einstein called spooky action at a distance. Remember, I went over relativity with you guys. Remember, one of the laws of the universe is that there's this cosmic speed limit, the speed of light, 3 × 10⁸ meters per second. You can't travel through space faster than that. Right? Now, there's some kind of sort of exceptions around the edge. Right? One of these weird exceptions is because of how the universe expands, universal expansion. If you get 2 galaxies far away enough from each other, they can travel away from each other faster than the speed of light. Right? That's why you have like an observable universe. And there's like stuff beyond it. We just don't know exactly how big the universe is. Is the universe infinitely big? It might be. Nobody knows. There's only so far we can see. But that's not galaxies traveling through space. That's just space expanding. So it's like, okay. So, and here's another one of these weird, like sort of exceptions. Right? So you guys remember angular momentum is conserved in the universe? Right? Well, what has angular momentum? Oh, well, little particles, electrons have angular momentum. Right? They have like spin. Spin is one of the properties associated with particles. Right? So suppose you entangle 2 particles. Okay, so bring them together, got 0 angular momentum, and then you separate them. Well, one's going to adopt one spin and the other the opposite spin. They're like up spin and down spin or something like that, right? Along one axis. Now, those spins, because we're talking about quantum mechanics, exist also probabilistically, right? Until you measure them, and then those spins fall into like one definite category. It's like spin up or spin down. Right? Now, here's the weird thing: is because angular momentum is conserved, once you measure one, the other has to have the exact opposite spin. But hold on a minute. We're seeing maybe 2 kind of contradictory things. If spin was probabilistic until you measured it, then, but once you measure it, it becomes definitive. Then how's the other become definitive? Always exactly the opposite spin, right? And what's really weird is that that happens instantaneously. That's to say, faster than the speed of light between the 2 electrons. So if you separated them by, let's say, like 1 light year, right? And then you measure the spin of 1, then you might think that information would have to travel 1 year to reach the other one because it's 1 light year away. But no, it's instantaneous. So if you had like 2 scientists measuring what's the spins, right, then they would get opposite spins and they'd meet each other in the middle and say, oh yeah, they were totally opposite spins. Okay? How does this information travel like faster than the speed of light is the implication here. That's why Einstein hated this idea. He called it spooky action at a distance. Well, but by the time that Einstein died around mid-century, there had been 2 interpretations of this floating around. One interpretation was that was when it was sort of exactly what I told you, which is where the story's leading. That measure 1, its spin becomes well defined, and the other immediately adopts the opposite spin faster than the speed of light. Right? But the other interpretation that was lying around that Einstein preferred, which would be more consistent with his own theories of relativity, would be along the lines of maybe there was hidden information that would have dictated what the spin ultimately would have been. So maybe it wasn't really probabilistic, even though the experiments seemed to indicate that was the case. But it was really just there's information that we had no way of knowing or accessing until maybe science advances or something. Right? And then, of course, they would always have opposite spins because of this information that we can't access, this hidden information. Right? Well, not so fast, because 1964, along comes this guy named John Bell, and he designs this really ingenious experiment. Now, I played you guys a Veritasium video a few minutes ago. There's a really, really good Veritasium video on this. I'm not going to play it for you guys because it's one of those videos that if you're really curious about this, please do go watch it. But you really have to sit down and like rewind the video a couple of times to really think really deeply about what's going on here. But I'll give you guys a good synopsis as I can here. Right. So John Bell was trying to test for, is there really this hidden information that would have dictated ahead of time how the electrons would have spun, and therefore you don't have to worry about this whole like faster than speed of light thing, or not, or was it really truly probabilistic, and we really collapsed the probabilities to like one spin definitely or another upon measurement. So we run back to the whole measurement problem, which ends up, by the way, spoiler alert, being the answer to this. What he did was he had these spin detectors in these 3 orientations at 120 degrees from each other, right? And say you had this pair of entangled particles, right? Well, if one was measured spin up from one detector, the other has to be measured spin down, as long as it's along the same axis. Now, along one of these other axes, you can do a little bit of trigonometry and figure out it would be probabilistically at spin up or down one or the other way, right? Now, if there was this hidden information all along, you can show mathematically, right? And again, go watch this video, right? But it's a Veritasium video. Really good job explaining this. you can show mathematically that they would only have opposite spins, or they would have opposite spins. It'd be more than 55% of the time. The fraction is like somewhere between 5/9 and 100% of the time, it would be opposite spins. Okay? But if the quantum mechanics interpretation of, oh, it's all probabilistic and then plots the curve, blah, blah, is true, okay, and they affect each other faster than the speed of light, then you should see it should be a 50-50 split exactly. So you go do the experiment and it actually ends up being 50-50 exactly, which again, like opens up this whole can of worms of like, how does information travel instantaneously faster than the speed of light? Because there was no hidden information. It was all random all along, right? Now, probably a lot of people's first thought, or maybe one of your first thoughts would be like, oh, well, could you use this to send messages, like send emails, like from here to Mars? You don't have to wait like a several minute delay that it would be. Like you just like bam, you get it right away. You just like collapse the universe down to a single point and just share information, right? Like faster than the speed of light. Even if no matter your interpretation of these experiments or whatnot, the catch is that this is all random information, right? So as to which way an electron is spinning, right? There's no known way to embed useful information like email or text onto those spinning electrons. So it would still be random. Okay. All right, fun thought here, fate and free will. So this is one of those topics that comes up in all over the place, that probably in a lot of your other classes, like how much free will do you really have? Maybe it's come up in possibly some books you read in English class, or maybe maybe psychology class. How many of you guys had psychology? Yeah, you guys. Yeah, do take psychology sometime. Hopefully, you guys get a chance to take this maybe at high school or college. One of these questions is like, how much free will do you actually have to determine your actions, your motivations, your opinions on things? Right? Well, if you, here, I'll pick a psychology example real fast, right? You guys know the story of like Pavlov and his dogs? Pavlov's dogs, like classical conditioning. Right? Yeah, right. Just in case you know, this is one of the most famous experiments in psychology. There's this Russian psychologist named, his last name was Pavlov. Right? He had these dogs, and he would like feed them like a certain time. Like, okay, it's 2 o'clock, and feed the dogs. Right? After a while, what he started doing was he would ring a bell and then measure the salivation of the dogs, right? And then feed them the food, right? And so when the dogs knew that they were about to be fed, they would start to salivate, right? Okay, so their dogs are ready to eat, right? And then he would always ring the bell before he fed them, and then always measure their saliva. And then one day he rang the bell but did not bring out the food, and measured the saliva of the dogs, and dogs were salivating, ready for the food. They had associated the ringing the bell with bringing out the food. So it's like, okay, so now I've got this. So that's called a classical conditioning. There's other kinds of conditioning too, like operant conditioning and other kinds. And it really gets to this idea of like, well, what actually affects your brain and your thoughts, right? And how much of this is environmental? Maybe it's more environmental than you think. I want to tell you guys another really like creepy experiment that I saw. Do you guys know? Vsauce, channel Vsauce? Right? He had this series called Minefield, and one of these episodes, this is absolutely crazy. So I have to tell the story. They did this experiment where they hooked up a participant to, I think it was like an EKG machine or something that reads your brainwaves, right? They had this box with a button on it, and all you're supposed to do is just very simply just press the button on the box. Okay, great. So okay, great. Right. But right, the story is about to expand. Right? Then that EKG machine was reading the brainwaves of the person, trying to predict when they were going to press the button, and then would ring a buzzer when they determined that the person was going to press the button. So after a while, the machine gets better at reading the brainwaves, and then so they press the button, hear a buzz. The machine's figuring out, okay, so these brain rings are associated with press the button. Okay, so it's got right. And then a few more iterations, they go to press the button, and then the machine would buzz before they hit the button. So and it became a race. Like, can you beat the machine to pressing the button? Right. So then they sit there, okay, this machine's getting really good at reading my brainwaves. Right? They try to fake it out. Like, okay, when do we press the button? Man, beat me again. Right. So they're sitting there, figuring out over the button. Okay, I'm gonna fake out this machine, and then the machine just starts buzzing. Right? And the implication, one interpretation of this is that because they would say like, oh, I wasn't even gonna press the button. I don't know why it's buzzing. But one of the interpretations, one of the implications is that subconsciously, your brain had decided, okay, I made the decision to press the button, and had just not made your conscious mind aware of that decision yet. But the machine picked up on the signals from your subconscious part of your mind that you couldn't be aware of, right? And then this then raises the question of like, well, where do any of your actions or decisions or opinions even come from? How much are they really yours, and how much are they just the product of your environment, whether you grew up in the country or the city, what media you expose yourself to, what books you read, what classes you take, who your friends are. Okay. And if you ask Isaac Newton, he would have been what's called a determinist. He would have said, well, free will probably doesn't exist because everything's just the laws of physics, right? So I've got this billiards analogy, right? You strike the cue ball, it's going to hit this ball into the corner pocket, right? Well, once you strike the cue ball, everything's in motion, right? Once you know the mass and velocity of each ball, like each particle, right? Everything that's going to happen in the next few seconds is determinable, right? Well, if your brain is just made of neurons, which are made of, like matter, everything else in the world is made of, why isn't your brain also follow like this analogy? And so we're just essentially a bunch of biochemical reactions, and we think we have decisions that maybe we don't as much as we do, right? Einstein also was a determinist. If you ask Einstein, what are you going to eat 10 years from now? He'd say, oh, that's already fixed in place, that in space time. It's already determined, like 10 years out, what you're going to do on that day. Okay? We're all just waiting to live that moment. Okay? So if there's any case for free will, one angle on that, actually, you could bring in quantum mechanics and say, well, because there is uncertainty, maybe that gives you like more of a likelihood to have some kind of free will. It's an interesting thought. So yeah, so you guys have fun think about that one. Standard model of particle physics. So just like the in chemistry, there's about 100 or so elements. You could say, oh, well, everything in this room is made out of that. Now you guys know from this class too, there's things like dark matter out there, which probably not on the periodic table, or even go to the periodic table. You can say, well, you could more simply break down every single one of those elements into just protons, neutrons, and electrons, right? So maybe it's really like three things, right? But then ask a particle physicist and say, actually, there's more than protons, neutrons, electrons out there. So electron is, you can call that a fundamental particle, but actually not protons or neutrons, weirdly enough. This you can actually break down into up and down quarks, and it's more than just those. So came up with this table of 17. So let me share my screen. Share screen 2. Okay, I bring up, oh, okay. Sorry, I have to dig through my folders a little bit and find this. Quiz, particle physics. This one right here. There we go. So, here we go. The standard model. All right, so we've got these 17 particles. Well, you could say 12 fermions. That's the purple and green ones there, and then 5 force carriers. Right, so 12 or 17, depending on how you count them. Right, and they each have a unique mass, charge, and spin. Right, and so just like a periodic table, you might classify them by like mass or atomic weight or something. Right, here you got mass, charge, and spin. Right. And what do you got here? Oh, I see electron is one of these fundamental particles. I see photon is. Up and down quarks make protons and neutrons, and there's also some of these other ones. Okay, so that's all good and interesting. Okay? Notice what's that kind of hovering off the table here, something called the Higgs boson, because I grabbed this picture off the internet apparently before 2012, because 2012 was when this last one was experimentally confirmed, right, the Higgs boson. Okay, so yeah, there you go. There's a standard model of particle physics. Now, the standard model, this is, how do they even know that those particles exist? Well, they know these particles exist from particle physics experiments that involve colliding particles together and then measuring all these spin, mass, and charge properties from the collisions. But they are probabilistic, right? So like you can't take a picture of any of those particles if they're too small, but you can measure experimental results from these collisions. Okay? And this model's been really successful explaining all sorts of physics, except for, weirdly enough, there's no connection to gravity. And that has a lot of scientists baffled of like, how's the real connection to gravity? There's a connection to the other three fundamental forces, which are electromagnetism, strong nuclear force, and the weak nuclear force. But gravity is actually not part of the picture. So there's still some unknowns that are not explained by the model. Now, I'll come back to gravity later. Right? I'm going to mention why that may not actually be a force even necessarily, but we'll get to that. Okay? But look at this this Higgs boson. There you go. Right. So that Higgs boson was the last to be experimentally confirmed. Now, what is this this boson? It's actually involves something called the Higgs field, which maybe I actually have to start with that. So there are these different fields that particles can interact with or not. And if a particle interacts with that field, then it has like certain properties. If it doesn't, then it doesn't. Okay. So one of these fields is called the Higgs field, and any particle that does interact with the Higgs field has mass. Now, mass, you might think, well, isn't that like just a property of matter? Something has mass, has inertia. Okay. Well, not necessarily. So not all particles have mass. For example, photons do not have mass because they do not interact with this Higgs field, right? Yeah, so from a particles physics point of view, you only have mass if you interact with this field. And then anything that does not interact with the field moves at the speed of light. Now, the speed of light is really the speed of all massless particles, right? But anything that does interact with the field and therefore does have mass necessarily moves less than the speed of light through space, right? Okay, oh, so there we go, got that. Okay. And what is this Higgs boson? Well, the Higgs boson is this Higgs field interacting with itself. And okay, when it has those mass, charge, and spin properties that showed you guys over on that table. Okay. And how do particle physicists know that it's there? Right? How do they verify this? Right? Again, you can't take a picture of this. What they do, I heard this analogy for trying to determine if the particle exists. It's trying to figure out what a piano looks like, but you can't look at the piano. The only experiment you can do with this piano is you can put it at the top of the staircase and kick it off the staircase. And as it's tumbling down the staircase, from all the way down, listening very carefully to how those keys are clinking, and saying, okay, well, here's what a piano would look like so that it produces that exact sound as it's tumbling down the staircase. And all you have to go off is the out of the file, right? And you can't really do that with a single piano. You have to have like millions of pianos, right? And then you have to put a model together and then check the model against all those individual experiments of pushing pianos down the staircase. And so collide atoms together. So there's this large hadron collider over underneath the border of Switzerland and France, so big. And they will smash atoms together at almost the speed of light, like 99.9 something percent speed of light. Okay? And then from these particle collisions, it's kind of pushing a piano down the staircase. They can get these results. Now, so this Higgs boson, and really all these particles are determined statistically. Okay? So let's go back to this probability curve, because we did some stuff with probabilities a couple weeks back, right? And this is one of those reasons. Okay? So in science, in general, how sure do you have to be before you publish your results? So statistics used all over the place in science, all different fields. Let's say you're in, I don't know, biology or economics, and you conduct some experiment, and it involves like thousands of participants, and you have some probability curve, right? And you want to know there's some phenomenon you're testing for, what you might call a null hypothesis. You want to know, is something happening randomly, or is there some phenomenon that would lead to that particular outcome that I want to test for? Right? And that's called the rejection of the null hypothesis. Right? A pretty standard, or a pretty common standard in most fields of science is approximately 2 standard deviations from the mean. So if you see some phenomenon happening, 2 standard deviations from the mean, that's somewhere roughly, depending on how you look at it, somewhere about 2 to 5% chance that it would be random, right? If you're getting some result consistently, that it would be usually about 5% random chance to happen. That's usually about strong enough that you can publish it in a paper and say, I've made some new discovery, right? Which actually raises a whole set of issues itself. It's like, well, how much published science is accepted as being some real result when really it just ends up being a 5% fluke. There's probably a lot of science like that. So oops. But when you get to particle physics, they have a crazy stringent standard. They have a 5 sigma standard. Do you guys remember those Z tables we were looking at a couple weeks back? Z tables. Remember, it only went up to what was the highest Z score? It was like 3.49, I think. Or so like 3.5 standard deviations from me, and that covered like 99.9 something percent of all possibilities, right? So get out the 5 sigma. When scientists say they've discovered a new particle like the Higgs boson, what that means from a probability point of view is that if the Higgs boson did not actually exist, then there would be something a 1 in millions chance that it was just a statistical fluke. It'd be like them winning the lottery if they discover something. So yeah, we can be like extremely certain that these particles actually do exist. Okay. Speaking of particles and particle interactions, something called Feynman diagrams. If you ever see a diagram that looks like this, pretty classic looking Feynman diagram. This is just a diagram to represent interactions of particles. So here's different kinds of particles you could have, and then I don't know why he puts time on the vertical axis, but this guy Richard Feynman came up with this idea. There you go. There's an example of a Feynman diagram. There are lots of them. You guys ever take like graduate level physics? Probably do. Lots of those. Right. Quantum computing. So little side shot here. Getting more side applications of quantum mechanics. So you guys know all computer files are digital. They're just like zeros and ones, right? It's a string of zeros and ones at the end of the day. Now, what is quantum computing? Well, quantum computing doesn't actually use bits. It uses what's called qubits. And what's a qubit? A qubit can exist in a state of superposition where it can be both a 0 and a 1 simultaneously. It's like, okay, so what's that good for? Well, if you have lots of qubits in a fully entangled state, then what this ultimately leads to is that the number of equivalent information you could have in qubits is 2 to the power of number of possible bits. So for example, if you had 2 qubits, could be a 0 or 1 for the first one and 0 or 1 for the second one, right? Now, once you measure it, it has to fall into one of those states. It becomes unentangled. Okay? But fully entangled, 0, 1, 0, 1, that's 2 times 2, that's like 4 classical bits worth of information. Okay? Now, because of how exponentials work, once you have 300 of these qubits, 300 qubits that are fully entangled, like 0 and 1 simultaneously, okay? That represents the 2 to the power 300 is equivalent to the number of particles that there are in the observable universe. Think of all the atoms that you are personally made out of, all the atoms, right? Which would be like crazy high number, right? And then for the entire planet, and then the entire solar system, the entire galaxy, then all the billions of galaxies that we can see, that's like 2 to the power 300. Okay. And okay, so what could this quantum computing be used for? Well, if you just want to do something like run a video file or play a song, then doesn't really give you an advantage. You just want to use a classical computer. But if you want to do something like crack a password or like solve some encryption or something, then this computing can go through crazy number of possibilities in a relatively small amount of time. Now, this might raise all kinds of security issues. I guess it's like any technology comes along, right? Creates new good possibilities and also its own problems that come with it. So there you go. There's the intro to quantum computing. This next one. Ooh, I like this one a lot. Okay, Maxwell's Demon and the Landauer limit. Okay, this one's crazy, the implications of this. So let me go back to thermodynamics. Remind you guys something about thermodynamics. You guys remember if you have a hot sink next to a cold sink? Let's say you have 2 aquariums filled with water, one hot and one cold. You need to leave them alone. Let's say it's a pretty well closed system. Come back a few hours later. That the hot should have some heat energy transferred from hot to cold, and now they both kind of lukewarm, right? But what you would never expect to see is if you started with 2 lukewarm tanks and then leave those and come back a couple hours later, that one tank has spontaneously delivered heat energy to the other. And now one heats up at the expense of the other one that becomes cold, right? That'll never happen spontaneously. And that's related to something called the second law of thermodynamics. Entropy would be going the wrong way in that case. That'll never happen spontaneously. Now you can force that to happen. You can take like room temperature air and force part of it to become cold and the other to become hot at that expense and dump that out. That's what refrigeration is. That's what air conditioning is. But that'll never happen spontaneously, right? Unless maybe you have like 5 atoms, maybe statistically sometimes that'll happen, but not with like billions of atoms, right? Okay. Well, there's this scientist back in the day named James Clerk Maxwell who laid down the laws of electromagnetism. He had these really 4 famous equations that actually were part of the inspiration to Einstein developing theory of relativity. Okay? And as a electromagnetism and thermodynamics were being developed around that time, late 19th century. He was think about this too. It had this crazy thought experiment. Like, what if you had two lukewarm tanks of water, right? And or air, but so lukewarm, right? And you had some character that had like universal knowledge that's perched above these two tanks. Right? We'll call this guy a demon. I don't know why demon exactly. I think it had just something to do with like a character with lots of knowledge, right? So this character has knowledge about the individual speeds of every single individual particle in each of the tanks, which is a lot of information, right? And if you're thinking about temperature, well, there's this kinetic energy theory of temperature. So like all the air molecules in this room right now, they're all moving at different speeds, but you could graph them on like a bell curve, and there's sort of like an average speed of particles, which correlates to the temperature in this room. And right, that's why you feel it being like such temperature, right? But if this character, this demon, has universal information about all the speeds of all these particles, and let's see, he also has control over a latch, like a door, and he can let particles through from one side to the other. Okay? Now, let's say there's zero energy involved in operating the door, so maybe it's spring loaded, so the energy that just open it, he gets it back when he closes it. I don't know. Right? Let's just take that to be a case. Okay? Okay. Then what you could do is you could let all the fast moving molecules to one side and all the slow moving molecules to the other side. And that would effectively heat up one side and cool down one side without expending any energy, which would look like it would violate the second law of thermo, which is one of those laws in physics that's flying around like sort of like begging to be broken. And this is the case where, hey, maybe this could actually be broken. And this has some crazy implications. Like what if the hot side, you heat it up to the point of boiling and you actually turn this into steam and that turned a turbine? Ooh, you know what you could do? You could run a whole power grid off zero energy, right? You wouldn't need any energy input. You wouldn't need any coal or any nuclear, right? You could just have knowledge operating an entire power grid, right? So this was an interesting like thought experiment that was lying around for about 100 years before anybody finally solved this and said like, oh, actually, you can't. This can't be the case. And how they actually eventually cracked. These people felt intuitively that this probably could never be a technology that could be developed. Although it'd be nice if it could, right? You just replace the demon with the computer. The computer could just create power for free, right? And the solution ends up being well, running something called the Landauer limit. Now, the Landauer limit says that there is this minimum amount of energy associated with one bit of info. It's 0.0175 electron volts, or about 2.8 zetajoules, which is a crazy tiny amount of energy. But here's the thing: this demon or computer system storing this information about how fast each molecule is moving. At some point, they're going to have to dump that information and clear that out and start over, right? And when you delete that information, that actually increases the entropy of the universe. And in fact, it increases the entropy in the universe more than the decrease in entropy by separating out the molecules. So yes, so the second law is of thermo is still safe even in this thought experiment because of this Landauer limit. Yeah. So another implication of this is that information is embedded onto physical systems, right? Like all the writing that I wrote here, it's not random scribbles. There's actually information embedded in like this writing, which in some way involves this Landauer limit, right? So information is physically embedded in systems, and there's an amount of energy that you can associate with that. And when you erase that information, that actually increases the entropy in the universe. Ooh, pretty crazy. Okay, superconductivity. Oh, here we go. So scientists around the early 20th century were testing out resistivity at different temperatures, right? Now, do you guys remember, did have you guys do this test? What is the resistivity of Play-Doh? Or I think I talked about it briefly, right? So resistivity, if you take that, multiply by like the length of the wire, divide by its cross-sectional area, you get the resistance in ohms, right? But resistivity is a material property. So copper has a certain resistivity, aluminum has a certain resistivity. You can make wires out of each of those, right? You can look them up in the textbook what those are. And resistivity of Play-Doh, if you did that experiment with the voltmeter and the blah, 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 right? Then you should get about 0.25 ohm meters, I think is what it is for resistivity of Play-Doh. Right? But it's actually dependent on temperature. Right? So now we're going back to this experiment. Oh, let me pause this video. Pause. All right, and resume. All right, here we go. So they're testing out how does resistivity depend on temperature. So they're making it colder, colder, colder. And they're watching the resistivity go down, which actually makes it like there could be a wire that's like better at transmitting electricity, like more efficient, the colder it is. Right? And then at some critical temperature, something crazy happens, something completely unexpected that nobody's looking for, which is that the resistivity and therefore the resistance went to exactly zero. Right? 0 ohm meters for resistivity, 0 ohms for the corresponding resistance. And this is called a superconductivity. Now, what is that critical temperature? Well, it's different for different materials, but it's crazy cold. Like the first materials that were discovered to have this property, it was in the single digits Kelvin or Celsius. So we're getting like really close to absolute zero. Now, in the meantime, there have been materials discovered that are like closer to room temperature, but not anywhere really near room temperature. You know, I think I got a graph on this. Switch my screen over and see if I can find this graph. Oops, not that folder, this folder. Superconduct. Oh, you know what? I got here. Let me pull up this. Okay, here's actual experimental data on this. Oh, whoops. Let me switch my screen for the Zoom recording. Oh, no, not that one. Got a bunch of windows going on here. You go share screen too. Right. There's what I was showing you. So resistivity is a function of temperature. Look at that, just like plummets down to 0 below this critical temperature. Now on this graph, it's close to 100 Kelvin. Right. Here's what I want to show you too is different materials going superconductive at different temperatures throughout different years they were discovered. So the first couple, it looks like a mercury and lead, but those are extremely cold. And so the closer room temperature, now 200 Kelvin, that's so crazy cold. I could like liquefy the air in this room. So it's not room temperature, but it's just not as cold as like 0 Kelvin. Looks like I've got some materials up here. Now the catch with some of these up here is like it says like 30 gigapascal, 150 gigapascal. So we're talking about crazy high pressure. So it's like, man. But if you could have something that went super conductive, say at room temperature, which scientists are still on the hunt for, engineers are still looking for materials to go superconductive at close to room temperature. That would be an absolute revolution because you would have like 0 energy loss in transmitting energy. You could have like a battery situation with this too, where you could have just a wire looped in on itself, and you could just have the current running in the loop and have 0 loss, and you just tap into it like 10 years later, right? Probably make wind and solar a lot more feasible, right? So you just tap into that energy when you needed it. Right? Quantum locking. So let me just for this. Switch my screen to. I'm gonna pull up a TED talk on this and just narrate this myself. Here we go. Quantum locking. All right. So look at this. Look at that. No, it's a superconductor there. Look at it floating around like a flying saucer. Right above that, there's a track of magnets down there. You guys see that? Right. Oh, what do you think all that smoky stuff is? You guys saw that like white smoky stuff? Do you think it's probably liquid nitrogen because you have to have extremely cold for this to happen? So he's talking about superconductors. Oh, look at that. That's a graph, like I just showed you guys. Right. Superconductivity. Now, magnetic field lines. You could draw magnetic field lines the same way Faraday did back in the day. Put iron filings near a magnet, they'll like line up from north to south. But in quantum mechanics, you can actually quantize those field lines, and you can call those fluxons. Right? And when you interact those field lines with a superconductor, superconductors actually expel these fluxons, these individual magnetic field lines. And there's an image of them right there. Actually, it's a video. Look at this. Look at those fluxons right there. Those are magnetic field lines. That's crazy, isn't it? Like discrete, quantized magnetic field lines. Okay. And a superconductor will expel those lines, and then you can have this quantum locking where these superconductors you can lock in place. Right? Here we go. Oh, look at that. Oh, oops. Get this door. Yeah, and it's not levitating in the sense of like being repelled from a magnet. It's actually like locked in place in those field lines. Oh, look at that. Yeah. What else can you do with this? You can put it on a track. Look at it flying around like a flying saucer. Ooh, look at there. Oh, Look at it go. And then finally, upside down. Oh yeah. Woo. It's quantum locked. Oh yeah. Quantum locking. So that one's fun. Run. All right, back here. Oh, lasers. There's this quantum mechanics explanation of lasers. I should tell you guys about a lot of these. I'm just going to explain as best I can, which is just stuff that I've read or seen on the internet. But if you want to get more detailed than any of these, then please do. Sure, you guys all got Google machines. So something to do with this. Now, laser light is not like regular light because laser light is coherent. It's in phase. Right. Right. Now, how do you get a bunch of photons to be coherent in phase and create this laser light? Right. Well, let's look at a bunch of individual photons. Remember, I have wave-like properties too, right? And say you bounce them between two mirrors. Now, you might think sometimes they'll be in phase and sometimes they'll be out of phase. But let's use this coin flipping analogy. Suppose you had two coins and you flip them. They might be heads, heads, tails, tails, heads, tails, or tails, heads, right? It looks like 4 possibilities, right? And if you want classical mechanics, there's a 1/4 chance of any of those happening. And those could correspond to be like being in phase or out of phase, like crest to crest. This could be crest to crest, trough to trough, crest to trough, trough to crest. You might say, well, everything just kind of balances out and this will never work. But in quantum mechanics, remember, if these photons are also have wave-like properties, it's kind of hard to distinguish between individual photons. They're all like these giant waves interacting with each other. So how the numbers actually play out is that there's more of like a 2/3 chance that they'll be together, like in phase, and only 1/3 chance that they would be like out of phase. So more likely they are, right? And that is the end result of that. Let's look at Hawking radiation. Okay, so black hole. What's going to happen with black holes? We'll leave them all around long enough. Now you might think, well, they're just crazy mass, crazy gravitational tug. Things just fall into them, and then that's like the end of those things, right? Also, if you go down the relativity path too, like time slows down to the point that it like nearly stops at the edge of a black hole. So maybe like time and space stop at the edge of a black hole. You want a black hole, you're donezo into the universe, right? But Stephen Hawking came up with this idea, and it's experimentally observed also that, well, there's this quantum mechanics angle that actually adds more to the story. So if you're out in deep space, let's say like between here and the next solar system, you say, well, what's out between this solar system and the next solar system? Maybe nothing, the void of space. Maybe you could argue like a couple of hydrogen atoms per cubic meter or something, right? But in quantum mechanics, there's also particles and antiparticles. That's what P and A is, right? Particle and antiparticle, that will spontaneously create out of nothing. But then what always happens, and that's happening in this room too, right? Particles, antiparticles being created out of nothing. But then what happens is they always just immediately annihilate each other. It's like they were never there to start with. So it's like, okay, well, it's just a wash. You can just ignore that, right? Well, not at the edge of a black hole. Edge of a black hole, right? The particle with positive mass, positive energy can possibly have enough energy to escape the black hole into the wider universe if it's pretty close to the event horizon. Whereas the antiparticle with the negative mass and the negative energy will more likely not have enough energy to escape. So it's more likely to actually fall into the black hole. Right? And when that antimatter collides with the matter inside the black hole, what it does is it slowly evaporates the black hole. So that's what Hawking radiation is. Hawking radiation is the particle half of the story leaving the black hole into the wider universe. So yeah, you wait trillions of years and black holes will eventually evaporate, which is a crazy long time span, right? The universe, the whole universe right now is only about 14 billion years old. So you're sitting around waiting like a trillion years for a black hole to evaporate, but given enough time, Hawking radiation will eat away, and that will be the end result. Okay. Radioactive decay, carbon-14 dating. Okay, so actually, let me do this. I'm going to skip over to this one first real fast. So they're considered to be 4 fundamental forces in nature, and these are them: right? Gravity, electromagnetism. In this class, we mostly care about this too. So gravity pulling you down to the earth. Electromagnetism is Oh, yeah. All right, see. Electromagnetism is almost everything else that's not gravity that we care about in this class. So like frictional forces, normal forces, like me holding up this pen, this electrons pushing against electrons. Obviously, you can do with electricity or magnetism. Right? But there are a couple other forces too. They're called, these are actual names from, not super creative names, but strong force and weak force. And these are nuclear forces. So if you ever say like, why would all the protons hanging out together in the nucleus? That doesn't make any sense from an EM point of view. Right? And electromagnetism is a lot stronger than gravity. Right? Okay, well, we're gonna tie this all to what's called the strong nuclear force. And the weak nuclear force has to do with this radioactive decay, which I skipped over and go back to that and talk about that. Right, so remember that standard model of particle physics, like those 17 particles, right? Those actually are able to account for these three right here. But weirdly enough, not for gravity, right? So where does gravity fit in this picture? I've seen a really good case made that gravity is not actually a force the way that these other forces are classical forces, right? So I'm going to make an analogy and then expand on that argument of why that could be the case. You guys remember something called the Coriolis effect? Right? So suppose you're on a merry-go-round and you have your eyes closed, but you're just like spinning around, right? Especially if you're on a huge merry-go-round or relatively small compared to it, right? You might think that there's a force pushing you out to the edge of the merry-go-round, but that's actually not the case. If you get off the merry-go-round and you look at everybody else still on the merry-go-round, from your new inertial frame of reference, you know that there is no centrifugal force. There's only a friction acting as centripetal force, like pulling everybody in, right? And it's just inertia and that whole story through with like rotational motion back in the day. Well, you can make the case that gravity is sort of like that. Like you think that it's a force, like centrifugal force, but really it's something else. So go back to a story that Einstein said back in the day. Einstein says that one of the happiest thoughts he ever had in his life was imagining a guy falling off the roof of a building. And here's why. He realized that as this guy was in free fall, like falling down, like plummeting towards the sidewalk, that person's physics would be indistinguishable from being just an astronaut floating around in deep space, right? So that person could be in an inertial frame of reference, and they wouldn't be able to tell the difference until, of course, they splat against the sidewalk. And then there was actually a normal force, one of these EM forces actually pushing against them at that point. What about those two? What if you're like in a rocket in deep space, just coast along, just inertia, don't you have your engines on? You're just just coasting, right? And at some point, you feel the tug of gravity from a planet, right? Well, you wouldn't know if you were just coasted along. You'd be like an astronaut, like that guy falling from the top of the building, until you kapow against the surface of that planet. But before that moment, the physics would be indistinguishable as to whether you're in that gravity field or not. So from Einstein's point of view, mass warps the fabric of space-time and creates this gravitational effect, but maybe gravity isn't really a force like GMM over R squared, right? What we think it is. It's just an artifact of the warping of space-time. So maybe gravity actually isn't a force, right? But the force that you actually feel is the normal force of like your chair or the floor right now pushing up against you. But if that's true, then that means that right now we are actually not in equilibrium, because there is a net force and the force is the normal force from the floor pushing up against us. And Einstein's interpretation of that would have been, yes, we are not in true static equilibrium. There is a net force on us, but it is pushing us through space-time. And that's one of the reasons why we perceive time as moving forward. So interesting ideas going on there, but there you go. There's an intro to these four fundamental forces. I should say too, there was an article, a science article that popped up in the last few months of there was some experiment that was done at one of these particle colliders. I think one in the States actually, where none of these forces could account for a particular experimental outcome, and it was a really subtle effect. But there's possibly more than just this going on in the universe. But let's look at one of these specifically. The weak force is usually associated with radioactive decay, right? So again, not all atoms are radioactive, but some are, right? And one of them is a particular isotope of carbon called carbon-14, which has a half-life of about 5,700 years. That means if you start off with like 10 grams of this carbon-14, wait 5,700 years, now you only have 5 grams of carbon-14, and the other half is decayed to, I think it's like nitrogen, and then moves on, right? Now, most carbon on the planet, like the vast majority, is carbon-12. There's a little bit of carbon-14, carbon-13 and carbon-14, these very rare isotopes. But all of us have carbon-14 in us right now, just in a tiny, tiny, tiny proportion. But it's a constant proportion. And it's that constant proportion as long as you're alive. And then as soon as you die, that carbon-14 starts dissipating and tends towards 0. Right? So for some reason, anything that's alive, organic matter maintains some proportion of carbon-14. Well, if you know that, and you know this exponential decay curves, you can put 2 and 2 together and figure out how old something that is dead is, if it started as being alive or made out of organic material. So suppose that you are an archaeologist one day and you dig up like some manuscript that's made of like paper or something. You're like, oh man, this looks like it's like hundreds of years old. I wonder how old this is. Well, you can carbon date it, and this carbon dating can go back accurately about maybe a few hundred, few thousand years, and then after that starts getting kind of inaccurate. But you go back so far, right? So here's like an exponential decay curve. So there you go. Right? Okay. We'll go back to that, but let's hit these last couple real fast and then show you guys some calculations with that. So unification. What are you doing on time here? We got so oh yeah, still got an hour of class left, so we're doing all right, but I'm getting pretty close to the end of my story here. Right, so one of the unsolved questions in physics is, can you unify the two different sets of laws of physics that are lying around? Right? This goes sort of back to, remember Schrodinger's cat, that thought experiment. So the 2 laws of physics, we got Einstein's general relativity, which is a more exact form of a lot of the like Newton's laws of universal gravitation, really turn out to be an approximation of that. Right, so we've got the macroscopic laws, general relativity. Now we've got these quantum mechanics laws that where there's wave particle duality, things exist probabilistically, get these like weird like quantum entanglement that spook the action in a distance, but this whole story, right? Could there be some physics that ties these 2 together and unifies these different laws? Right? One of the proposals on the table is something called string theory, right? And then string theory goes back to the 1970s, and there are mathematical models that say, well, if you express everything in terms of tiny, tiny strings on the order of magnitude of a Planck length, then that can actually build up and be consistent with everything in both these sets of laws, both quantum mechanics and macroscopic physics. Right? There were 5 different string theories that were floating around back in the day, but at some point someone realized, oh, actually there are 5 different mathematical perspectives on the exact same phenomenon. They've been all tied together and called collectively M theory. As far as I know, nobody knows what the M stands for, but that's what it's called, M theory. And it does involve lots of extra dimensions. So depending on how you count them, you can get 10 or 11 dimensions. So our brains are good at perceiving about 4, right? We've got 3 spatial dimensions, and then time, we call it like 4 dimensions of space-time, right? So string theorists, people, proponents of this say, well, there's actually a lot more dimensions, and run the math and do a bunch of matrix mechanics and blah, blah, blah. You explain everything this way. Now, one of the problems with string theory is that nobody's been able to come up with a good experiment to test this. Remember, if you are conducting really good science, you need to be able to come up with a falsifiable experiment. And nobody's been able to do this yet because the strings we're talking about are so like crazy small. It's like so still a question out there. Could be some kind of unification. But suppose we figure out unification one day. I mean, the future's a long time. Yeah, with master quantum mechanics and technology, could you at some point say, could nanotechnology develop to a point where you could have a molecular assembler? So this is an interesting engineering question. Here's a fun story. What if you want to bake a cake, right? So the way you bake a cake now is, well, go to the store, get some flour, get some sugar, get some water and oil and an egg, throw it all together, and then put it in the oven, and great, you've got a cake. Great. But if you want to purchase from a physics point of view, you could say, well, that cake is really made out of these certain types of atoms. We got carbon atoms, we got nitrogen atoms, we got oxygen, we got hydrogen, maybe a little phosphorus, right? And certain arrangements. Could you have like little nanobots, like rearranging all these atoms So you just pour in those base ingredients. Like I'm gonna like pour in some water and blah, 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 right? And then hit a button on a machine, and then it just rearranges it into a cake for you, and out pops the cake. So maybe in principle that could be the case. Will this be a technology that we could have one day? I know this has been floated in a bunch of sci-fi stories. Like Star Trek, they had this type of technology. You just press a button, you can get whatever you want. So maybe. Now, one question I would have is I would want to know, like, I wonder how energy intensive this would be, right? Like, would it take a crazy amount of energy to make that cake, or would it be something more reasonable? Because if you're living on a planet with finite resources, that might be one of the issues to be have to tackle too, right? All right. Then last year here, gonna wrap up the story. When you revisit this half-life with carbon-14 dating, just show you guys a little bit of the math. Okay? So I'm going to use two different models for radioactive decay. One that's maybe more intuitive for half-life, and then one that's more like proper mathematical. Right. So start with this one. A equals A naught times 1/2 to the power of T over T 1/2. Right? What is this? Right. So the amount of substance that you have is equal to the initial amount of substance, and I'm talking about a radioactive substance, so it's decaying, right? Times, right? Now, every time you multiply by a half, wouldn't that be like one half-life is passed, so you only have half of what you started with? Okay, and then if another half-life passes, you need to multiply by half again, and then again, and then again. Okay, so that's why we're taking 1/2 to some power. Now, what is that power? T over T 1/2. Okay, that's like a count of the number of half-lives. So, for example, 5,700 years is the half-life of carbon-14. What if 5,700 years have passed? 5,700 or 5,700 in this exponent, that's a count of exactly one half-life, which means you multiply half one time. You guys see how this equation is working? Right. What if 11,000 years have passed? That would be like 2 half-lives, wouldn't it? Because 11,000 over 5,700, that's like 2. 1/2 to the power 2, that's a half times a half. Now you're down to a quarter of what you started with, right? You guys see that? Okay. Well, okay, so if you know how much substance you're starting with, like so many grams, right? Then here, we've got this table. So the number of years that have passed, look at the number of years that just did integer multiples of that half-life of 5,700, right? So we've got how many half-lives? 0, 1, 2, 3, 4, 5. Okay. Then how much substance should you have? Question for you guys. I bet all you guys know the answer to this question. What is 1/2 to the power of 0? And it's not 0, it's what? 1, right? Okay, so if you run 0 times pass by, 1/2 to the power of 0 is 1. So A equals A naught, doesn't it? So you start off with the initial amount. So we came up with a very nice number for this example. They get half that is that, half, 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 half. See, it keeps growing half. Okay, so every half-life that passes. Okay, so you guys see like the big picture model, how this is working? Okay, now suppose you are an archaeologist one day and you're actually running problems like this. You're probably going to not use this this more intuitive 1/2 to the power something, but you probably see this E. Right? You guys know this E from a math class. This is one of these famous mathematical constants. It's irrational, kind of like pi. It goes on forever, but no repeating digits. But the first few digits go like this, like 2.71828. Right? And I know one of the applications of E, and you would know this too if you were in a calculus class, or if you took calculus this year, is if you graph y equals e to the x, looks kind of like this. So on a y-x axis, this could be y equals e to the power x. And this is the only graph that E is 2.71828. Okay. This is the only graph where the slope of the graph at any point is the y coordinate of the graph itself. For example, this crosses through the point 0, 1, like that is a coordinate on this graph, right? E to the power 0 is 1. You guys just told me that. Okay? But if you take the slope of this curve at this point, which would be like, here's the tangent line, right? So what's the rise over 1 at that point? I know this is 1 over 1. And I know that because that is the y coordinate of this graph at that point. Okay? If you did e to the power of something and got 2, then the slope at that point would also be 2. Rise over 1 would also be 2. E to the power of a negative number. Guys, a power of a negative number, that doesn't make the number negative. That makes it a fraction, doesn't it? Here, show you guys an example. What is e to the power of, well, here's e to the power of 1, 2.71828. Yay. What is e to the power of -1? And it's not a negative number. it's a decimal. It's 0.367 something, right? Right? Is it? Okay, that could be like right here, right? So see, it goes like right? Okay. So that's one of the properties of E anyway. But we're not looking at exponential growth. We're actually looking at exponential decay, which is like the opposite of this, right? So I'm going to replace x with t for time, and then y I'll replace with a, like the amount of substance, right? And we're going to get something that looks like this. This is exponential decay. Actually, it would start at time 0, which would be like right there, right? Right on that curve. It looks like this curve just mirrored. If you just mirror that curve, look like this, right? It's going to tend towards 0. So after you wait like 1,000 years, you get like almost 0 left of that substance, right? Okay. This could take the form a equals a naught. So here's a naught right here times e to the negative t, some version of that. Okay, is that? Except instead of negative t, I'm going to do one more thing, say negative kt, where that k is related to the half-life of the substance. So let's chase down what is that k. For carbon 14, here's what you do. You say after 5,700 years, so I'm going to plug in 5,700 for the time, right? I'll end it with half of what I started with. You can solve for k and you get a number. Great, it's a tiny number. There we go, 1/years. Okay. Then you can create this more proper mathematical relationship and plug in that k value, which is always true for this particular substance, right? And now you can try again. So after, let's say after 22,000 years, how much substance do you have? Well, we have the answer already. It's right here. We know 16 grams based on this more intuitive model, right? But plug in this newly discovered k value, blah, 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 get the exact same answer. So this number are the same. Okay. All right, finally, to close off this whole story, suppose you're archaeologists in the field, and you're trying to do half-life radioactive carbon dating, right? You actually wouldn't do any of what we've done so far, which is I told you how much time has passed, and I'm actually asking how much substance is left over. You would be having the exact reverse situation of you pull up some organic material from back in the day, and you would be able to run get a measured count of how much carbon 14 it has, and you want to back calculate how much time has passed. That's the whole point of this process, right? So that's the last one. It's like, what if you know some organic material alive that's like 10 microgram per cubic meter of carbon 14, and then you dig up something that has 3 microgram per cubic meter of carbon 14. That tells you that somewhere between 1 and 2 half-life has passed, because between 5 and 2.5, right? Right. Run all this math, right? Logarithms, exponents. Oh, look, natural log. You guys remember natural log from one of your math classes, right? Which is like the like the opposite of E, right? E and natural log are opposite processes. Right? You can come up with the number of how old the substance is, and for this example, I came up with about 10,000 years old. Ooh, look at there. All right, there you go. There's a quick crash course on quantum mechanics. Hope you guys learn something new last day of school. And if anything in that intrigues you a lot, then please do go home and look that up. So that is a wrap on this whole class, because today's last day of this class. But yeah, it has been a fun journey. I've enjoyed teaching you guys a lot, and it's been a really great year. And hope you guys have an awesome summer and great senior year. Oh yeah.